The Big Bang is a concept that has shaped our understanding of the universe, forming the foundation of modern cosmology. According to Einstein's theory and what is known as textbook cosmology, the Big Bang was the moment the universe began its expansion, marking the creation of all matter, energy, space, and time. This event occurred approximately 13.8 billion years ago and gave rise to the vast universe we observe today. However, recent developments in cosmology suggest that the Big Bang might not be the absolute beginning. Instead, there could have been a phase before the Big Bang that was equally important in shaping the universe as we know it. This earlier period is known as cosmic inflation. Inflation is one of the most intriguing aspects of modern cosmology, proposing that before the hot, dense phase of the Big Bang, the universe underwent an incredibly rapid exponential expansion. During this period, the universe was doubling in size at a mind-boggling rate. To illustrate just how extreme this expansion was, if the universe began smaller than an atom, it would have grown to be significantly larger than the entire observable universe within a tiny fraction of a second, about a millions of a second. This expansion phase did not last long, but it played a crucial role in shaping the cosmos. When the inflationary phase ended, the energy driving this expansion was dumped into space, heating it up and creating the particles of matter that make up everything we see in the universe. In many ways, inflation is the precursor to what we now think of as the Big Bang. While the theory of inflation is widely accepted in cosmology today, many unanswered questions remain. For instance, we do not yet know what started inflation in the first place, what caused it to stop, or how long it lasted. These are open questions in cosmology, and answering them is crucial for a deeper understanding of the origins of the universe. Before inflation, the universe was an incredibly dense tiny point of matter, often referred to as a singularity. From this singularity, the expansion began and eventually led to the formation of atoms, molecules, stars, and galaxies. The idea of the Big Bang as the beginning of everything is appealing, but modern cosmology suggests a more complex picture. Some theories propose that the universe underwent a phase before the Big Bang, during which inflation caused the universe to expand at an exponential rate, doubling in size at least 80 times in a fraction of a second. This rapid expansion was fueled by a mysterious form of energy that permeated empty space. When inflation ended, the energy that had powered this expansion was converted into particles, heating the universe and leading to the hot, dense state we call the Big Bang. This inflationary phase was cold and empty, but it set the stage for the creation of matter and the universe we observe today. One of the more speculative ideas in modern cosmology is the concept of eternal inflation. This theory proposes that inflation did not stop everywhere at once. Instead, it stopped in patches, creating many different regions or bubbles, each of which could be a universe in its own right. Our universe would be just one of these patches. According to eternal inflation, there could be an infinite number of these universes, each with its own set of physical laws and constants. This is where the idea of the multiverse comes into play, the notion that our universe might be one of many or even an infinite number of universes. If this idea holds true, it might explain why our universe is so finely tuned for life. In this multiverse scenario, every possible combination of physical laws could exist in different universes. We happen to live in one where the conditions are just right for stars to form and for carbon, oxygen, and other elements necessary for life to exist. While theories like eternal inflation and the multiverse remain speculative, the concept of inflation itself is grounded in experimental evidence. The strongest support for inflation comes from the cosmic microwave background radiation, CMB, the oldest light in the universe. The CMB was released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. At that point, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially take a baby picture of the universe. The light provides clues about the universe's earliest days, helping researchers understand what happened right after the Big Bang and offering support for the inflationary model. One of the most significant discoveries came from the European Space Agency's Planck satellite, which took detailed pictures of the CMB. These images reveal subtle variations in the temperature of the early universe, and these variations match the predictions made by inflationary theory. This experimental support strengthens the idea that inflation is not just a speculative theory but a crucial part of our understanding of the universe's origins. Understanding the Big Bang and what came before it requires a unification of two of the most important theories in modern physics: Einstein's theory of general relativity and quantum theory. General relativity describes the large-scale structure of the universe, including the behavior of galaxies, stars, and planets. Quantum theory, on the other hand, describes the behavior of particles on the smallest scales. To answer the ultimate questions in cosmology, such as what space and time are and where the universe came from, scientists must develop a theory that unites these two frameworks. This would allow us to understand not only the Big Bang but also the conditions that led to it. One of the more surprising aspects of the universe is its size. The most distant objects we can observe are about 47 billion light-years away, meaning the observable universe is about 94 billion light-years across. This might seem counterintuitive, given that the universe is only 13.8 billion years old. How can the observable universe be larger than the time it would take light to travel in the age of the universe? The answer lies in the fact that the universe has been expanding throughout its history. As the universe expands, the distance between objects increases, making distant objects farther away than the time it would take light to reach us. Most scientists believe that the universe extends far beyond the observable universe. In fact, it is possible that the entire universe is infinite in size. The observable universe is simply the portion we can see, limited by the amount of time light has had to travel since the Big Bang. There could be vast regions of the universe that we will never be able to observe. While it's possible the universe is infinite, the question remains: is there anything beyond the universe? Most scientists are skeptical of this idea. If the universe is infinite, there is no beyond. The universe would simply go on forever. Even if the universe is finite, it might not make sense to talk about anything beyond it. Space and time are properties of the universe itself, so the concept of beyond the universe may not have any physical meaning. Just as the beginning of the universe is a subject of intense study, so too is its eventual end. The best current estimate is that the universe will continue expanding forever. This is due to a mysterious phenomenon known as dark energy, which is causing the expansion of the universe to accelerate. Before the discovery of dark energy, scientists believed that the expansion of the universe would eventually slow down due to the gravitational pull of matter. There was even a possibility that the universe could stop expanding and begin to collapse, leading to a big crunch. However, dark energy seems to be pushing the universe apart faster and faster. If this acceleration continues, the universe will keep expanding indefinitely, eventually reaching a state where galaxies drift so far apart that they become isolated from one another. In this scenario, the universe would become cold, dark, and empty. Stars would burn out, galaxies would drift apart, and all matter would eventually decay. This is sometimes called the Big Freeze or heat death of the universe. The story of the universe, from the Big Bang to its possible end, is one of the most profound and complex narratives in science. While we have learned a great deal about the origins of the universe through the theory of inflation and the study of the cosmic microwave background, many questions remain unanswered. What caused inflation to begin and end? What lies beyond the observable universe? Is there a multiverse, and if so, how many other universes exist? As scientists continue to study the universe using advanced technology and theories that unite quantum mechanics with general relativity, we will undoubtedly gain deeper insights into these mysteries. The journey to understand the universe is ongoing, and each discovery brings us one step closer to answering the ultimate questions of our existence. The exploration of the universe's origins and structure is not just a scientific endeavor. It also invites philosophical questions about existence, reality, and our place in the cosmos. One major area of interest in cosmology is the nature of dark matter, which is thought to make up approximately 27% of the universe's mass-energy content. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Understanding dark matter is essential for explaining the formation and behavior of galaxies. Recent experiments and observations have provided insights into dark matter's properties, but its exact nature remains elusive. Various candidates have been proposed, including weakly interacting massive particles, WIMPs, and axions, but so far no direct evidence of dark matter particles has been found. The search continues through a combination of terrestrial experiments, astrophysical observations, and simulations that model how dark matter influences the large-scale structure of the universe. Another critical area of research is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy constitutes about 68% of the universe's total mass energy content. Its discovery was unexpected and has led to numerous theories, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is pivotal, as it shapes the ultimate fate of the universe. Researchers are studying the effects of dark energy on cosmic structures and seeking to determine whether it remains constant over time or evolves. In addition to dark matter and dark energy, the study of cosmic structure formation offers valuable insights into the universe's history. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments, have revealed how matter coalesced under the influence of gravity, leading to the intricate structures we see today. Simulations run on supercomputers help scientists understand how these structures formed over billions of years and how they continue to evolve. Astrobiology also intersects with cosmology as scientists seek to understand the conditions that allow for life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has intensified, with thousands discovered in recent years. Some of these exoplanets lie within their stars' habitable zones, where conditions may be right for liquid water to exist. By studying these distant worlds, researchers hope to learn more about the potential for life elsewhere in the universe and what it requires. Moreover, the role of fundamental physics in cosmology cannot be understated. The quest for a unified theory that combines general relativity and quantum mechanics continues to challenge physicists. Theories such as string theory and loop quantum gravity attempt to bridge these two realms, potentially offering explanations for phenomena like black holes and the early universe. As technology advances, so does our ability to observe and interpret cosmic phenomena. Space telescopes like the James Webb Space Telescope are revolutionizing our understanding of the universe by providing unprecedented detail of distant galaxies and cosmic events. With each new observation, we are piecing together the puzzle of the universe's formation, evolution, and ultimate fate. In conclusion, the study of the universe encompasses a rich tapestry of scientific inquiry and philosophical reflection. From the fundamental forces that shape cosmic structures to the search for extraterrestrial life, our exploration is a testament to humanity's enduring curiosity about the cosmos. As we strive to answer these profound questions, we gain not only knowledge but also a deeper appreciation for the vastness and complexity of the universe. The interplay between observation and theory is crucial in cosmology. Innovations in technology, such as advanced detectors and machine learning algorithms, are enhancing our ability to analyze astronomical data. These tools allow scientists to sift through vast amounts of information, identifying patterns that could reveal insights into cosmic phenomena. One significant area of research is gravitational waves, ripples in spacetime caused by catastrophic events such as colliding black holes or neutron stars. The detection of these waves has opened a new window for observing the universe. By studying gravitational waves, researchers can gain insights into the nature of these extreme events and test theories of gravity in ways that traditional observations cannot. Additionally, the concept of cosmic time is intriguing. Unlike our everyday experience of time, which is linear and uniform, cosmic time is influenced by the dynamics of the universe's expansion. This raises questions about the nature of time itself. Is it an absolute entity, or does it depend on the observer's position and velocity? Such philosophical inquiries parallel scientific explorations, highlighting the multifaceted nature of cosmological studies. The formation of the first stars and galaxies, known as the cosmic dawn, is another critical focus. Understanding this period helps illuminate how the universe transitioned from a hot, dense state to the rich structure we see today. Observations of high redshift galaxies provide clues about the processes that occurred during this formative era, helping scientists piece together the timeline of cosmic evolution.